Hi there, Mr. Sutton here, bringing you the Algebra 2 6-7 lesson on modeling with exponential and logarithmic functions. This will be a two-parter. In part 1, we're going to be writing exponential functions using 2 points, and in the next part, we're going to determine and write exponential and logarithmic models for data based on doing it by hand from a table and also using a little Desmos. For our first question, we're going to be writing an exponential function that goes through these two given points. Now, it is important that they're spelling out that this is an exponential function, because otherwise this could be any type of function, including a linear function if you just have 2 points. So once we know it's exponential, we're going to start this off by writing a couple equations. And to do this, we're going to use ab to the x equals y, the standard exponential form. So specifically, we're going to plug each of these points into this form, and that's going to give us two different equations. And I always start with the second equation here. So we're going to do ab to the third power equals 54. So again, we're using ab to the x equals y. And then for my first point, we're going to do ab to the first power equals 6. Now, once we've got these two equations, we're essentially going to be solving a system of equations for a and b, and then we're going to plug those back into this original form, and that'll give us our equation. But how do we solve this system? There's a few ways to go about this. One way is that you could isolate one of the variables and then plug it in for the other one and do it that way using the substitution method. There is kind of an elimination method that we can use, though, when we have all multiplication here. What we're going to do is we're actually going to divide these equations to cancel out the a value. So I'm just going to put a big fraction bar under here to kind of show this. And this is going to cancel out my a's. And then we have b cubed divided by b to the first. Subtracting, that's going to give us b squared. And then 54 divided by 6 gives me 9. Now, it's important to note that normally we don't divide by variables because you might be dividing by 0. So you might be wondering, well, how are we allowed to get away with this? And the crucial point here is that we have this equals with something that's not 0 on the other side. If this AB stuff equals 6 and not 0, that means that neither A nor B could be 0, because if one of them were, then it would equal 0, not something else. So we're guaranteed that we're not dividing by 0, which is why we can get away with this. Now, once we've got A gone, we're going to basically solve for B, and that'll be our next step. So since this is just b squared equals 9, we can take the square root of both sides, and that'll give us b equals 3. And once you've got your b value, you just have to plug that back into either of these equations. That'll let you solve for a, and then you'll have an a and a b that you can plug in to write the actual function. So at this point, pause the video and see if you can finish this one off. Now, since I have a choice of these two equations to plug my b value of 3 into, I'm going to choose the easier one, the one that has b to the first power. Either of these will work, but I'll have less work to do if the exponent is smaller. So I'm going to use this one and have a times 3 equals 6. And then all I have to do is divide by 3 to get a equals 2. Plugging that back in then, we can write y equals 2 times 3 to the x. And that's our final exponential function. So here are two more points just to give you a little more practice with that process. Pause the video and see if you can come up with an exponential function that goes through these 2 points. All right, so just like before, we're starting with ab to the x equals y and plugging in my 2 points. So for the first one, for the first equation, I'll use my second point here. And the reason I'm doing the second one first is because that's the order that I'm dividing things in. It's kind of like when you find the slope of something in linear form, you do second point minus first point. Same idea here. So we've got a times b to the second power equals 12, and a times b to the first power equals 3. And then we'll divide those. A's are going to cancel. B squared over b is just b. 12 divided by 3 is 4. And we actually don't even need to take a square root this time because the exponents were only 1 apart. So we ended up with b to the first after dividing. So that's kind of nice. Plugging b back in, again, I'm going to use the simpler equation. we have a times 4 equals 3. So therefore, dividing by 4, we get a equals 3/4. And then plugging all that back in, we have 3/4 times 4 to the x power for my exponential function. Just to mix things up, this time around, we're going to do the same sort of process, but we're going to give you a graph with 2 points on it. So pause the video and see if you can come up with an exponential function for this graph. All right, so we could use some other points on the graph other than the ones they gave us, but it's good to use the ones they've spelled out for us because we know those for sure. Others we might just be kind of guessing at or estimating. So we are using our ab to the x equals y sort of paradigm again. And I'm going to do ab to the, let's see, I'll use my further along point here. So ab to the 4th equals 4. And then I'll use this point back here. So ab to the 1st power equals 1/2 or 0.5. And let's just divide these like we've been doing. A's are canceling. B to the 4th over b to the 1st is b to the 3rd, b cubed. And then 4 divided by 0.5 ends up being 8. Well, now to solve for b, I have to take the cube root of both sides. Good thing we did a few lessons on solving things with exponents that aren't just the 2nd power, right? So the cube root of 8, which ends up being 2. So one thing you might be noticing at this point is that we always end up with a positive b value. I mean, here we did because it was an odd root. On the first example we did, though, you might have been wondering, well, why didn't we have a plus or minus when we took the square root to find the b value? And that's because of the format of exponential functions. B has to be positive for it to be an exponential function, so we're not even allowed to consider negative b values. So we can discard that negative root when you're solving for b. All right, so going back now and solving for a, again, I'll use my simpler equation. So we have a times 2 equals 0.5. And then 0.5 divided by 2, or 1/2 divided by 2, that's going to be 0.25 or 1/4, however you want to call that. Plugging that back in, we have y equals 0.25 times 2 to the x. So at this point, we have reached the end of part 1 of this lesson. Pause the video and try out some practice problems writing these exponential functions, and then join us back when we take a look at identifying what type of function something is and using a little bit of technology. Welcome back to part 2 of this lesson. So we're going to start this off by taking a look at a table and determining by hand the type of function represented by the table. There's ways to do this by graphing it on technology, namely Desmos, and then doing different regressions, but it's always good to know how to do this without a calculator just in case. So the way that we're going to do this is there's 2 simple tests we're going to run whenever we see these tables here. One is looking at common ratios, the number that I get when I divide each of these y values by the number preceding it. Exponential functions, it turns out, because you're multiplying by the same thing over and over again, exponential functions, the output of an exponential function, has a common ratio. Again, you keep multiplying by the same number. So if we go through all of these and we see that we're multiplying by the same thing to get each successive number, that would tell us this was an exponential function. Now this might not be the case for every table you look at. So we also have polynomial functions, and it turns out that the output of a polynomial function, which we've seen in past lessons, has a common difference where you keep adding the same number. Now you might notice this kind of at the top level of a polynomial function if it's a really simple one like a line, but you might have to find a few of these common differences, common differences on common differences all the way down, as far as this thing goes. The number, the level of common difference in one of these tables, first, second, or third, that's going to tell you the polynomial's degree. So if you find that these numbers, for example, had a common difference or didn't, but then their common differences had a common difference, that second degree common difference would tell us that we had a second degree function, a quadratic. So this is the basic idea. Look at common ratios and common differences and use that to figure out what type of function we're dealing with. With all that said now, here's a table for us to look at. Pause the video and see if you can figure out, using this type of reasoning, what sort of function is going on here. All right, so we could try common differences, but If we do that, we see that we got 0.5, 2, 4, and then 8, and then we've got another common difference that's 16. So if you keep trying to find common differences on those, you're going to see that there is none. It just keeps going up as you go. So we also want to look at common ratios. 1 divided by 0.5 is 2. 2 divided by 1 is 2. 4 divided by 2 is 2. I mean, we're seeing a pattern here, right? We've got a common ratio of 2 here. 2 times 8 is 16. 2 times 16 is 32. Since we have a common ratio, that proves, based on the data that they've shown us anyway, that this has to be an exponential function. Here's another table for us to play around with. Pause the video and see if you can determine the type of function for this table. All right, did you take a look at common ratios? So 8 divided by -1 is -8. 7 divided by 8 is, well, not -8. So you don't have to keep going. Like once you've found that the pattern breaks after 1 or 2 tries, you can just move on to the next test. Let's next test out common differences. So 8 minus -1 is going to be 9. 7 minus 8 is going to be -1, which is not the same as 9, but we might be able to find common differences down another level or two, so let's keep going. 2 minus 7 is -5. -1 minus 2 is -3. 4 minus -1 is 5, and then 23 minus 4 is 19. No common difference at this point, but these numbers kind of look like there's some sort of pattern going on. So let's find the common difference of the first difference. Let's find the second difference. -1 minus 9, that's -10. -5 minus -1, that's really +1, so that's going to be -4. -3 plus 5 is 2. 5 plus 3 is going to be 8, and then 19 minus 5 gives us 14. Still no common difference, but still kind of looks like there might be a pattern. Let's try it one more time. -4 minus -10, that's really +10, that's 6. 2 plus 4 is 6. 8 minus 2, that's 6. 14 minus 8 is 6. So it turns out we have a common third difference. That means that this is a third-degree polynomial that's being shown to us in this table. This is going to then be a cubic function. On this next problem, we have a table here showing us the numbers y in thousands of people who are visiting Machu Picchu, which here's a picture up here, Machu Picchu, X years after 1990. So this first year is 1990, this is 1994, 1998, and so on. They want us to use technology to determine if the data here fits an exponential model, and if so, write an exponential function for it. And if all of these conditions are met, use this model to estimate the number of visitors in 2020. So 2020, that would be 30 years after 1990, so that's actually not given in the table. Otherwise, we wouldn't need to estimate it, right? So the idea here, we've already done modeling and regressions with polynomial functions and other types of functions. We're going to do the same steps we did for those. We're basically going to enter our points in the table here into a Desmos table, and then we're going to go down and use exponential regression. It's one of that drop-down list. So pause the video, see if you can remember how to do all that, and then we'll bring it back and I can walk us through it. All right, let's go to Desmos. All right, so I've pulled up Desmos. If you forgot, we have to make a table by hitting this little plus sign here, and then go to table. And let me make my x values first. So we got 0, 4, and these are going up by 4s up until 28. Remember, if you just press enter after the first two, it auto kind of does that for you, keeps adding the same number to give you a consistent x spacing. But always check your table and make sure it is actually consistent like that, and in this case we see that it is. Now I have to get my y values in there, so let me do 150, 210, 360, and then let me move this so I can get the other side here. We also have 470, 700, another 700, 1150, and 1580. And at this point, once you've got all of those, it's a good idea to press this little magnifying glass to get a zoom fit and actually see the points that you just graphed. And then we'll click this little line up here that adds the regression. Now, we've done this before with lines and all sorts of polynomials. If we go to our drop-down menu here, we see that there is also an exponential regression, which we will click on, and we get a nice little curve fit with an exponential function. Now, it's always a good idea to take a look at your r squared. The closer this is to 1, the better a fit this is. 0.98 is pretty good. So just kind of cutting and pasting what I had on there, that's what my graph looked like. We can see that this is a pretty close fit, so we can call this exponential. It's not precise, but it's probably about as good as you're going to get for most of these real-life situations. And they wanted us to write a function for that. So the function is just right here, the equation, 172.6612 times 1.08182 to the x, all of that. We can just copy that in here and maybe round it off a little bit if you want. And then they wanted us to use this model to estimate the number of visitors in 2020. So that means we basically have to plug in 30 for our x value here. So f of 30, let's see what that comes out to. Now, a trick that we've seen before in Desmos, if you want to do it on Desmos, is you can actually click this little equation button here to export that down to an entry below. And if I rename this as f of x and then go down another level, that allows me to plug in anything I want. Let's do f of 30 and see what we get. That's about 1,827.448. So just in terms of what the real life model was, this y value was in thousands. So if I move this decimal 3 to the right, I see that in 2020 there were approximately 1,827,448 people. For our last problem, we got a little bit of reading to do here. So the atmospheric pressure decreases with increasing altitude. I guess as you get higher, there's less pressure pressing down on you. At sea level, average air pressure is 1 atmosphere, which is this crazy number of kilograms per square centimeters. The table here shows some air pressures at several altitudes. So the air pressure is the input, the altitude is the output. They want us to use technology to find a logarithmic model of the form h equals a plus b times ln of p that represents the data, and then estimate the altitude when the air pressure is 0.75 atmospheres. So really, this is just a fancy way of saying, hey, put this in Desmos and use logarithmic regression, and then plug it in. So this is going to be a lot like the exponential regression, just choose logarithmic regression instead. Pause the video and give that a test drive. All right, let's see how it went. So just like before, I need to put my data in a table on Desmos. So let's do that. We've got, let's see here, 0.55, and it auto-completes to 0.1, but that's not quite correct. We're going to have to enter the rest of the x values manually. And let me just move this over so I can see the rest of them. We've got 0.12, 0.06, and 0.02. And now for the y values, we're starting with 0, 5, and 10. And then that moves on to 15, 20, and 25. Now you might be saying, wait a sec, I see a pattern. Our y values are going up by 5s. It's the x's that are kind of irregular. Well, I mean, that's actually kind of tracks because logarithmic functions are the inverse of exponential ones, and you're interchanging the input and the output. So I guess it makes sense that it would work out this way. Let's go ahead and zoom fit this stuff. So there's our function, and let's do our regression. Now instead of choosing exponential, we're going to choose logarithmic regression. Make sure you don't mix it up with logistic, which is quite a bit different. So logarithmic, and there it is. And we see our r squared is a high degree of fidelity here, 0.9926, so it's definitely very logarithmic in pattern. Let's see, here is the graph that I just drew, and the function, let me go back and see that. It looks like we've got 0.862658 minus 6.44738 times ln of x, all that. And for the rest of the problem, they just wanted us to estimate the altitude. So to do that, we just have to plug 0.75 in for p and see what that comes out to. And we'll use our trick, like we've been doing, of clicking this little button to cut and paste our function down here and changing this to f of x to make it easier to plug stuff in. and then we'll do f of 0.75, which comes out to about 2.717, and that is going to be, let's see here, what are they doing the altitude in? In kilometers. All right, glad I checked. So about 2.72 kilometers. So that's it for this one. Thanks for coming along for the ride. Until next time, Mr. Sutton, signing off.